Okay, so yeah, so I'll code from here on out just to demo some stuff. So one of the things I mentioned in the first video, I talked about how you can, a nice shortcut that we have, which is to pound include bits standard C plus dot H, and using namespace standard and int, not typing well today. Okay, so kind of a base setup. And what I wanted to do first of all was talk just about like ints and long ints and stuff like that. So just as an example, let's say we've got int x, and here's a number that's near the maximum size. So you get about 1 billion. So 1, 2, 3, 1, 2, 3, 1, 2, 3. So that's nearly the maximum size integer that you can have. So I'll make y and z. And if I add all three of these together, we can see how this stuff, what things look like. So I'll define an integer a, which is x plus y plus z. X. Okay, so there's a program. I'm just creating 3 integers, each one about 1 billion. That should fit in there. I'm going to run it and print everything out. Probably going to make lots of little typo mistakes. So we'll just make sure that this works. And if I run that, what I see is I get the correct answer for x, y, and z, but I had an integer overflow when I tried to add these into a. So when I added a, x plus y plus z, I got integer overflow. Everything died. Now, if I think if I just add 2 of them, that one still fits barely. But yeah, so if I just add 2 of the things together, it worked fine. Now, the solution that we talked about last time is you want to use a long and set a long integer to do that. And so you might think, okay, this is going to solve it, right? A needs to be long. Now it's big enough, it can hold the sum of those 3 numbers. And so I go out here and I run the thing, and I still run into the same problem. Okay, now, why is this happening? Anyone in the class here know? Yep, exactly. So the problem is over here on the right-hand side, I do these additions and everything is still an integer. So when I add an int to another int, it's going to store it in an int. And then I add another int and it's still in an int. And so what I get over here has already had integer overflow as an intermediate step before it got assigned to a long. So I need to cast one of these to a long, or I can just actually, make one of these long up here. If I want to, that would solve it. There's a few different ways you can do it, but as long as I actually cast one of these, and actually, I forget order of operations, so I'll use some extra parentheses. But now if I run this, everything works fine. Okay, the long integer is big enough to hold the sum of the 3. But I had to make sure that all the intermediate operations also got held correctly in there. So a typical way that you would do this is you would instead of doing that, I would just make everything long int. And a lot of times people will pound define something so that they can, they'll actually, if you're not used to doing this, and I always forget how to do it, LL as long. Okay, and then write LL. You make a mistake there. Okay, so quick example there just to see just to see how this whole thing works. So you can see it again. I can define this long, and I can define my type as long. Some people even go as far as to redefine int as being a long. I wouldn't do that. That can create some other problems along the way, although most of the time, 99% of the time, it'll actually do the same thing. But anyway, just be careful of doing that. Okay, any questions on this? That makes sense. That was something that we talked about last time. So the next thing I want to talk about are different ways of reading in data and calling a basic sort. So I will get rid of all this stuff. Okay, and so what I'm going to do now is I'll show you just a few different ways that typically you read stuff into a vector or an array or whatever else you have. Common ways of doing it. So I'll just define a few variables in ij, and I'm going to, in fact, let me show you before I go too far. So I've created a test data file, and the test data file has a number 10. It says I'm going to have 10 numbers, and then I've got 10 numbers here, and they are the odd numbers from 1 to 19. It's just the odd numbers from 1 to 19 in random order. Okay, so all of this is, easy. I mean, this is just going to be the test data that I use. So now I need something that's going to let me read that in. So I'm going to have an integer n that holds the number. I'm going to read in n, and then I'm just going to have some sort of loop that lets me loop through and stick everything into an array. So basically, there's going to be there's a few different ways we can do this. So one is I can create an array of integers. So I can do a, and I can say it's of size n, and just declare it that way. And then I can just read everything into the array element itself. Okay, so I'm going to just output everything after I've read it in. That's what this loop at the bottom is doing, is it's running through the n items. It's going to output each one at a time, followed by a space, and then there will be an error. Hopefully there's not an error. So if you're not familiar with input redirection in Linux, hopefully everyone is by this point. But if not, if you have another file, so in this case, the files I have one called test.in. So I'm going to redirect test.in into the compiled one, which is called a.out. So test.in is just my input. So if you have something, if you only want to write your input one time, stick that in a file, and then you run your executable, and left arrow redirects the input from test.in. And if you want to if you want to direct the output somewhere, you can use a right arrow to test.out. Okay, that would output everything to a file called test.out in that case. Okay, but in this case, I'm going to do that. So I read everything in, I printed it out, everything worked fine. Okay, I just read into an array. Now, if I wanted to, I can sort this array. I can sort the elements of the array, and that's the sort algorithm. So if I've got it in an array form, if I've declared a static array like this, I can write a plus n, and that's all I need to do. Okay, so what these actually are is a is a pointer to the beginning of the array. A plus n is a pointer to the element right after the end of the array. So like if I start at 0 and I go forward to element n, I'm now right past the end. Okay, so you always output the beginning and right past the end. Okay, and so now if I do this same thing and run it, I now get the same list, and it's all been sorted correctly. Okay, any question on that? Okay, I do see one online. I thought you couldn't initialize an array with a size not known at compile time. Yeah, so that might actually be part of the C++ standard, but they usually let you do it anyway. So yeah, it compiles like you just saw here. But you're right. Sometimes it won't let you do that ahead of time. But most compilers will let you specify. But it's static. You can't change it later. You can't adjust the size of the array. So once it's declared, it has to be known at the time. The size has to be known at the time it's declared, but it doesn't have to be known at compile time. Okay. So yeah, it can fail compilation. In this case, it didn't. Okay, so a more common one, and the one I would usually use myself, is going to be the vector. And so we'll create a vector of ints, A. And in this case, if I know the size, you can definitely declare the size right here. And this creates the vector of size A with n elements. I will mention that if you want to initialize the array, like say you wanted to initialize everything to 0, you can pass that as a second parameter. So if you're not familiar with doing that with vector, easy way of declaring a big array, initializing it all with some value. The first element is the number of elements. The first parameter is the number of elements. The second one in the constructor is the initial value to give every element. Okay, but I'm going to read everything in. The exact same loop I had before. And my sort has to be different. So I have to do a.begin and a.end. And that should sort the whole thing. So if I try this, getting random junk phone calls during class. If I run that, if I compile it and run it, again, everything works, everything's sorted. There are other ways of doing this, and just to kind of show you what they are, if you, for some reason, don't know the size at the beginning, like this. For instance, well, I'll take it one step at a time. I'm going to input everything into a number j, and then I can just do a.pushback and append it onto the end of j. And this is nice and efficient for an array. So we could do the entire thing this way. Again, I'm just going through n elements since I knew how many there were to begin with. I'm pushing each one onto the back of the array, and then I'm going to sort it. And again, I should just do 2 windows, but I don't know how to do that and let everyone online see it. So I do the same thing, it still works. Now, occasionally, you will have something where I'm still going to, just so I can reuse the data file, I'm still going to read in n, but let's pretend that I don't actually know how many elements I'm going to read in. Okay, that I didn't have a number 10. I'm just supposed to read elements until I run out of elements to read in. Okay, if that's the case, I can rewrite this loop, and I can just write while cnj. Okay, and what's going to happen here is this is going to call cn, try to read something into j. If it ever fails, if that doesn't work, then this is going to be false, and the loop will exit. That means you've hit the end of input. Okay, if it was unable to read anything in because it hit an end of file. If it didn't hit an end of file, then it reads something into j, and you go ahead and you push that back. So notice here, I don't actually need to know n. I still read it in because it's in my test data file. I don't need to know n. I can sort everything. I can change the way I output stuff. So, so here I'll say for x equals a.begin. X equals a.end. X plus plus. And instead of outputting a sub I, I'll dereference x. Okay, now I need to actually declare a type for x here. As I go from the beginning to the end of this this array. I mean, another way, hang on, before I do that, a different way I could do this is I could always do a.size. I will say one thing to be a little bit careful of is every time you call the loop, it's checking size. So you can very slightly optimize your code by storing the size, assuming it's not going to change in something and just accessing that. But it's not much different to go through to use the function call because I think it's inline. So you can do things like that and loop through item by item. But the other option is we can go through here, and it's common to use auto. If you're not familiar with auto, it'll automatically tell you the data type. So just to make sure I haven't made a mistake so far, let me do this. Oh wait, I need to say I'm using C++. Did I have a mistake in there? Oh, yes, I did. It's not equal. Okay. So everything compiled fine there. And then if I run this, it still works. Okay. I think there was one thing. If you don't want to do that, I think the way you can do it, instead of saying it's type auto, the type would be a vector int iterator. I think that's right. I usually use auto for the. Okay, you get the same thing. All right, so all of that was just different ways, trying to show you a lot of different variations of how you can read stuff into an array, how you can call sort on it, and all of that sort of thing. Let's see, what did I want to do next? Okay, one more variation with respect to sort. So there's lots of ways you can do this. I will say the way I do it is probably not the most efficient way, but it's the way that makes the most sense to me. So I will just show you the way I would normally handle this. But there's better ways. There's like 3 or 4 different ways you can do this in C++. But if you want to change your sort command, you can create a function that I'll call it greater than. So I'm going to sort in the opposite order. And if I have a const int %a, const int %b, and I'm going to just return. This is a function that you should return true when a is less than b. Okay, but I'm going to return b less than a. So this is basically going to sort in the opposite order for me. Okay, there's other ways you can do this. So that's my comparison function, and I just add that in as the third parameter here, that function to the sort routine. Okay, so if I want to change my sort command, I want to create my own comparison function, and this is especially useful if you have some sort of class or structure. You can create your own comparison function. And there's a couple other ways to do it. Like I said, there's functors, and you can create classes that have the default operator, and you can use lambda functions, and there's other things you can do. But this is the way that just I find the easiest to think about. So this should sort order. Yeah, so now it's going from greatest down to smallest. Okay, so I changed the sort. If I wanted it to be like a normal sort, so something that's exactly the normal sort, I would write a less than b. So this returns true if a is less than b and false otherwise. Okay, or another way of doing it is if a is less than b, return true, else return false. Okay, so this is like a standard sorting. This is what a normal person would do. So if I run this, I should get everything in a standard sorted order. If I go back and change the order here, then I should get it in reverse order. Okay. Question? So like within the call to sort? Yeah. So you can. That's one of the other methods I mentioned. So instead of creating a separate function called GT, you can actually write a bunch of stuff here that I always mess up. So I always have to look it up anytime I want to do it. So that's why I don't usually do it. But yes, there are ways of putting these like inline comparison functions and things like that in there. Yes. Yep. Okay. I do see an online question. Will this one be posted on Canvas? I will try to put this one on Canvas just in case, or a link on YouTube that you can look at through Canvas in case you find it useful.
I have a question.
On this part so far.
I had a question.
Yeah.
So that GT function, is that taking like every pair like in A and like comparing it?
Yeah, so what GT is doing is it's saying, I've got a function that's taking two integers, and these are constant references. So you can either have a, like a literal or a variable or whatever. So I've got two integers, A and B, and that's what I need to compare is whatever A and B are. So if I had some other class or struct, if I had something like this, something like that, I could create another version here called that takes in my structs. And do something like if x is equal to y, then I can do any bizarre thing I want to here. I have no idea why you would want to sort this way, but
wouldn't you have to do like a dot x equals a dot y or something like that?
Yep, sorry.
Yeah, okay.
Yeah, thank you. I said x and y, I meant a and b. Something like that.
Can you also do a function that has like more than two parameters?
You only want to have one that does two parameters, because basically this is the comparison function. So like if you remember back when you learned sorting routines, it's based on how many comparisons you make. And so it's basically using this comparison function every time it needs to, regardless of what sorting algorithm gets used, assuming it's a comparison-based sort. This wouldn't work for like a radix sort or something like that. But if you're doing any comparison-based sort, and there you're only comparing two things at a time. So you would only have two parameters. And you return.
Okay, thank you.
Yeah, and you return true if the first one is less than the second one, and you return false otherwise. So that's what the function should be. You always return true if the first thing is less than the second one.
Okay.
All right. So the next thing I wanted to mention was a little bit about how we can search and find stuff here. So let's see. I'll stick with the vector version here that we have just to kind of show how it works. And I'll get rid of this sorting with greater than and just show a standard sort. Okay, so one thing I can do is I mentioned that there is a find command. Find will tell you if something is in the array or not, and it works whether it's sorted or not. So for now, let's not sort the thing, and I will say if find a dot begin. Actually, sorry, I'm messing it up. I think it's a dot find, right? A dot find. Okay. And let's say we're trying to find the number 7. Okay, so if you remember, 7 should be in that test data that I have. And so now I can say if x is equal to a dot end. So if it basically, what this is a linear search. Okay, so all I'm going to do here is check to see if the number of 7 is in this array. Okay, so this find command will takes in the beginning, the ending, and then the thing you're looking for, and it returns an iterator. And the iterator should either say that it found it or not. Okay, so this is again is a linear search. It's going item by item. It can work on an unsorted list. So notice I took the out there. So if I compile this thing and I run it, it found it. It found the number 7. And I believe I should be able to dereference it. So I believe if I dereference that, it should actually show me the value that I had. So I found it, the value is 7. So I was looking for 7, I found it. Notice that 7 was just somewhere in the middle of that array. It wasn't sorted. So it was just doing a linear check. It was checking the first one, the next one, the next one, the next one. And if it got all the way to the end and it didn't find anything, then it failed. And so that's where I say not found, is if the iterator that got returned was the one at the very, very end. Now, if I'd been looking for something that was not in there, like 8, okay, an even number, I'd do that, it's not found, okay, because it went through every one of them, the iterator hit the end, nothing was found there. Okay, next thing, if I want to use a binary search. If you want to use a binary search, you have to have a sorted array. So you have to sort everything first. And if you remember, the thing that we're going to use is not find. It is lower bound. And what lower bound does is it gives an iterator to the next thing, or to the first thing equal to or greater than the one you're looking at. Okay, so in this case, right now I have, oops, that's not good. In this case, if I'm looking for 7, what I can do is I can say now, the question is, if I'm at the end, I will say, the number that I was searching for was bigger than everything in the array. That's the only time that the iterator will be at the end. Otherwise, I won't say I found it, but the value of lower bound is X. Okay, so if I run this thing again, I was looking for the number 7, and indeed I found it. So lower bound, the iterator it pointed to indeed came out to be the number 7. Value of the lower bound is 7. If I instead tried to look for something like 8, see, and I did it again. Okay, now it says the value of the lower bound is 9. And the reason why is it did a binary search, it didn't find 8, so it returned the next thing bigger, which is 9. Does that make sense? Okay, so if you want to do a binary search, in other words, a login search instead of an order in search, first you have to make sure you have a sorted array. Second, use lower bound, and then you can check something at the end of that and say, am I actually at the lower bound or not? Okay, I guess there's one other thing to mention. There is a command called lower bound, but it is not there is a command called binary search. The binary search is not actually giving you the lower bound, but sometimes people will use it. They'll say if binary search of a dot begin, a dot end. So in other words, if it exists, this will be true, and if not, it'll be false. So if it's true, then I would go ahead and I would say, I would print this thing out. This, okay, get rid of all this stuff down here. Here, I'll say, okay, so, so now the code is clean again. So if I do a binary search, I'm looking for the number 8. If I find it, then I can actually call it again and get the answer out of there. Close parentheses. If that's not the case, then I am going to output not found. So 8 should not be in here. I should get a not found in this case. What did I do wrong? Left off another parenthesis. Okay, so 8 was not found, but if I was to look again instead for 7, then it works. Okay, so that's just to demo how those two things work. So we've only got about 10 minutes left. Man, I was afraid I wouldn't get through all this. I'm not going to. I want to show you, let's see. I want to show you there's a few things I wanted to still show you. Pairs, stacks, queues, priority queues. Let me go with stacks and queues and priority queues real quick, just to show you how those work. So I'm going to get rid of all this binary search stuff here. Okay, but I'm going to leave in something that prints it out. Yeah, question. Yep. Yeah, so the question was, well, if you have to sort your thing first, you're doing something n log n, doesn't that counteract the advantage of the order n operations? So yes, but imagine you have to do n searches. So if you're doing n searches, it's faster. It would be n squared in one case and n log n in the other. But yeah, that's a good question. If you're only doing one search, you don't want to bother sorting. You might as well use find. But if you're going to do lots and lots of searches, doing the binary search is going to be faster overall. Okay, so let's go with an example here. In fact, let's start out with a queue. If you're not familiar with them, queues, we can read in numbers j again and just push them into the queue. There's no sorting of the queue. And so we can say we can basically go through everything that's there and say, well, the queue is not empty, so not a.empty. We can print the thing on the front of the queue. So it would be a.front. And then we have to pop it off of the front. Okay, so quick example of doing something with a, well, I guess I'll leave that for the moment. So we're just reading in numbers j, we're pushing each one into a queue, and then we're outputting the queue, so it should come out in the same order that we read them in. So if I take this, I compile it, and I run it, I get things there. And if I look at my input file, those numbers are the exact same order that I read them in. Okay, if I wanted this to be a stack instead, so if instead of a queue, it was a stack A, I can just push everything onto there. Again, it's while A empty. The only difference here is instead of front, I write top, and I look at whatever's on top. And now you see they're in reverse order. Okay, so just like you would expect with a stack. If I do a priority queue, okay, remember this is a heap underneath. It's always going to pull out the largest value. Okay, so every time I put something into the priority queue, then when I look at whatever's on top, it's going to be the biggest value. And then if I pull it off, I get the next biggest value. If I pull it off, I get the next biggest value. Okay, so the way that would look is you get everything basically in reverse sorted order from largest to smallest. Okay, highest priority item was the biggest thing you put in there, then the next biggest, and so on. So basically, you've got to reverse sort using a priority queue in that case. We can, if we want to, although it's kind of messy, you actually can modify the priority queue to use a different sorting function. So I will just show you what that looks like. It looks something like this. What is it? It's type GT, something like this. Oh no, I might mess this up. Okay, and so this is using the greater than. You have to give it a couple of extra parameters as you declare the priority queue, including something that's the function type that you have here. And again, you can use other functors. It's a little bit easier. And then you pass in the parameter, which is the comparison function to use. So this will create a priority queue where the comparison function now is GT, I think. Whoa, it might work. Yeah, okay, and it goes from lowest to highest now in that case. I will say that feels to me like I always have trouble remembering that. If I hadn't looked this up shortly before class, I wouldn't have even remembered to how to type that in. So I find it just personally, I find it easier to write something like this. And every time I push something in, if I want to just reverse the order, I output -J, and then I negate it every time I pull it out. And that way it's reversed the order automatically. There's other ways you can do this that are pretty simple also. That type of hack is a simple way of also getting something that's priority queue in reversed order. You just negate all the priorities, okay? Okay, but that's like a total hack. You would never ever want to do that in a real job or something, right? So, okay, in the last 4 minutes, I ought to stop just to be on the safe side here. Well, I'll try one last thing. Okay. So one last thing that I'll show you is how the pairs work. So there's a pair that's built in. Pairs are sometimes returned from STL functions, but you can use them a lot in your own. In this case, I'm going to have, instead of a priority queue of ints, I'll create a pair of ints like that, and I will have a vector of pairs of ints like that. Okay, so A is going to be there, and what I'm going to do is just go ahead and read in half of the data. I'll just go half the data and I'll read them in as pairs. Okay, and then down here I'll copy that and I will output A sub I Okay, so instead of reading in like 10 numbers, I'm going to read in 5 pairs of numbers, and I'm going to put them in as pairs. So remember that the pair, the first thing in it is always whatever dot first, and the second one is always whatever dot second. So you can assign to it just like it's a structure. You can do all of that. So if I click, probably, let me just see if it worked, but it doesn't because of probably what you said. Thank you. Yep. Okay, so there's the pairs that I read in. So they come in pairs each time. And the nice thing about pairs is if I want to, once I have this whole thing, I can just sort them just like always. I can sort my vector just like before, and it always sorts on the first number and then the second one. So if I do the same thing and run it, you'll notice it got sorted based on the first index in the pair. So if you have like a priority queue of pairs, sometimes you have the priority and then you have the thing that you want to keep track of. A pair is often an easy way to do that. So you can use the priority as the first thing. That's what gets sorted on. And the second thing is the thing that you need to keep track of or print out or whatever else it is. Okay, so our time is 15 seconds from being up, so I'm going to stop there. I won't give an example of tuples because they're ugly anyway. I might do a quick example of this next time, depending. I'll try to see if people found this useful or not next time when we also go over the problem set. So lab this Friday. The two key differences from this past week. One, it's going to start automatically at 2 o'clock. So be ready to go at 2 o'clock, either in class in person or online. As far as online, I'm going to try to figure out a better way to handle people needing to answer questions online, because we could not get people to do breakout rooms. It appears only I can assign breakout rooms, even if I make people co-host. So as a result, I think we will try something a little bit different, but I'll let you know what that is if you're one of the online folks, or if you're in here and are going to be online on Friday. The other difference is last time I ordered the problems easiest to hardest in some sense. This time you'll just get a set of problems to work on. There's no ordering, so you'll need to read them and decide which ones are easiest and hardest. You can look and see what other people are answering to get a hint of what might be easier or harder, but that's not even a guarantee. Okay? Any last questions before we go? All right. Well, have a good rest of the week. Good luck with stuff. Remember, there are office hours with the TAs over the next couple of days. And see you in lab on Friday.